When planets pass close to the Sun, their orbit is affected by Einstein's theory of general relativity and Newtonian gravity. Predicting this orbital shift is known as precession in celestial mechanics. Einstein was able to predict a shift in Mercury's orbit 102 years ago, proving his theory of general relativity. As planets get closer to the Sun, their velocity increases, which means relativity's influence becomes more prominent. Jupiter's gravitational pull, called the Kozai mechanism, also shifts planetary movement by making their orbits more elliptical, meaning they move closer to the Sun. The Kozai mechanism has created bright sun-grazing comets, since they become bright and burn more gas as they approach the Sun. A recent study from the University of Oslo analyzed how Jupiter's gravitational pull changes orbital patterns in conjunction with general relativity. Some planets or comets may be pulled so close to the Sun that they ultimately collide. A comet called 96P Mach-1 will exhibit this effect when it collides with the Sun 9,000 years in the future. 96P Mach-1 can have a solar shift 60 times more significant than Mercury's, setting a new record. The comet also reverses direction because of Jupiter's gravitational pull, which is known as an inclination flip. When studying impacts with craters, the effects of general relativity and Jupiter's periodic gravity must be mathematically factored in. Jupiter's gravitational pull could determine whether or not solar bodies collide. Craters left by previous collisions between the Earth and other bodies are useful in uncovering evolution and how the Earth physically responds to such incidents. Current predictions for collisions between the Earth and known comets and meteors may be improved by reevaluating them to account for the combined effects of Jupiter's gravity and general relativity. Isaac Newton's law of universal gravitation states that every particle with mass attracts other particles. Furthermore, gravitational force increases with an object's mass and is inversely proportional to the square of the distance between two objects. Most gravitational forces of everyday objects are negligible due to their relatively small masses in comparison to the planet. The force of gravity between two objects is equal to g, the gravitational constant, times the mass of the first object, times the mass of the second, divided by the distance squared. G equals 6.6742 times 10 to the negative 11th. The fundamentals of planetary orbit were discovered by Johannes Kepler, who developed three laws. He first states that planets orbit in an elliptical motion around two foci. For our solar system, the Sun is one focus. Kepler's second law states that orbiting bodies sweep out equal areas in the same amount of time. In other words, when a planet is closer to the Sun, it creates a wider arc length in a set amount of time than when it is far. Kepler's third law states that the square of the period of an orbit increases proportionally with the semi-major axis cubed. The semi-major axis is the radius at its longest point. In action, this law means that the further a planet is from the Sun, the longer it takes to complete an orbit. Einstein combined his special theory of relativity with Newton's theory of gravity to develop his general theory of relativity. Special relativity explains that the speed of light in a vacuum is constant regardless of the speed of an observer, and that the laws of physics hold true for non-accelerating observers. General relativity involves space-time, a four-dimensional continuum. The theory states that gravity is a distortion in space-time created by bodies with lots of matter and energy. His theory has been validated by its ability to predict the bending of light around massive objects, black holes, the expanding universe, and alterations in Mercury's orbit. General relativity is more accurate than only using Newtonian mechanics to approximate times, locations, and events. For instance, it accounts for the fact that time passes more quickly when you are at a higher altitude since the force of gravity is weaker.